Welcome to today's FDTD Go16 Applications webinar. Today we're pleased to have Nancy Ramos leading the presentation, and she's from TAFB, NHC down in Miami. She's going to discuss Go16 new capabilities for tropical forecasting and analysis in the NHC TAFB. So Nancy, if you can go ahead to the next slide.
Sure.
Just a few things to cover here before we let Nelsie begin. All of these are recorded, and if you want to see any of the past ones, these are available on the webpage given here. Also, call for speakers if you're interested in leading one of these Go16 webinars for the future. Just let us know. Go ahead to the next slide. And finally, a few protocols to go over. We'll give about 20 minutes for our speaker. And you can either send questions via the GoTo chat, or at the very end, after Nelsie is done speaking, we'll take a question and answer period over the phone here. We'll end in less than 30 minutes. Please remember, don't put your phone on hold, and also mute your phone when not talking. So at this point, I'll turn it over to Nelsie.
Thank you, Dan, for the intro. Good morning, good afternoon, everybody, depending on the time zone you are. Like Dan mentioned, today I'm going to talk about some of the Go16 applications utilized in TAFB during the hurricane season and during the winter. TAFB is the Marine Division of the National Hurricane Center. We generate analysis and forecasts over the tropical and subtropical Eastern North Pacific and North Atlantic. And some of our main products include the high seas and offshore water forecasts, tropical weather discussions, surface weather and forecasts, and gridded marine forecasts. Our products include marine warnings for gale, storm, hurricane forecast, force winds, and tropical cyclone-related conditions, as well as information on reduced visibility and other marine hazards. Our area of responsibility, our broad area of responsibility, extends from 20 south to 30 north between the Prime Meridian and 140 west. Our purple box in this upper left image shows our area for the tropical weather discussion in the Atlantic and the Pacific. The one at the bottom shows in the dark blue shade the high seas area of responsibility in the Pacific. And the one on the right, the light blue, shows our offshore zones, and combined with the dark blue is our high seas in the Atlantic basin. During the hurricane season, one of the main synoptic features we analyze and track are the tropical waves. Besides describing the strength, position, and movement of the waves, the associated convection, as well as any potential impacts to land masses or marine interests are discussed. Here we chose an image of the tracks of some of the storms during the 2015 Atlantic hurricane season that, as we know, it was one of the 3 consecutive below average Atlantic hurricane seasons. And one of the main reasons for the lack of cyclonic activity during that season was the constant and extensive Saharan air layer over the Atlantic low latitudes. The dry and dusty air associated with the south act to weaken the waves by hindering the development of deep convection. Here at the top, I show 2 of the Meteosat 8 split window RGB images on July 2nd, in the morning of July 2nd, or around 15:30 UTC. With the 12C TAFB analysis overlaid. The one at the left highlights the Saharan dry air, while the pseudo-natural imagery at the right shows like a brown haze that is indicative of Saharan dust. The imagery shows how a train of tropical waves are being affected by the salt and dry air and dust. Tropical Storm Ida is one of the tropical cyclones during 2015 that was severely affected by the dry air and dust. It does originate as a tropical wave that moved off from Africa on September 13. It underwent cyclogenesis on the 18th at 6C, and strengthened to a tropical storm on September 19 at 0C. However, dry air and dust intrusion along with strong westerly shear weakened Tropical Storm Ida to a tropical depression on September 24 at 6C, and to a remnant low on September 27 at 12C. The RGB's composites above, along with the 12Z analysis, TAFB analysis, shows the moment when Ida is undergoing weakening to a tropical depression, partly due to the dry air and dust entrainment to the right imagery. And the imagery on the right shows the dust plumes in color pink, and you can see here how the dust intrusion and the dry air to the left is weakening Ida to a depression. Another product that we use to monitor the tropical wave environment is the SSMI total precipitable water, and most currently the CETA layer precipitable water, especially from the surface to 850 millibars or lower levels. Here's in the image to the upper right-hand side. This imagery helps us to analyze horizontal and vertical moisture gradients and give us a qualitative interpretation of moisture. LPW has better represent dry and moist areas, which has translated to areas of devoid of convection or where convection is taking place. And it has shown to more accurately depict the wave environment. Here we have an example. To the right we have the layer LPW, and it shows that we have some dry air to the northwest of the wave, while the total column of SSMI shows more moisture. If we look at the Ghost 13 IR at that time, we can see that the LPW is more representative of the convective environment that is undergoing those tropical waves. Now I'm going to show some of the actual Ghost 16 imagery utilized during the 2017 hurricane season, in particular for the short-lived Tropical Depression 4 that lasts 42 hours. The picture that I'm showing is a GeoColor imagery of the Depression 4 on July 7th, racing west of a Saharan dust storm, as we can see here. This is a proxy imagery, like a very similar imagery, I can say, like the pseudo-natural imagery, but in the Ghost 16 we have, of course, more highlight feature, and we have higher resolution, and we can see some features better than with the pseudo-natural. This is during, it still was a Depression 4. I'm going to show here some of the history of the Depression 4. TD4 precursor came off the coast of West Africa on June 28 around 11:45, and while moving towards the Central Atlantic, the CETA layer precipitable water at the low levels and the RGB imagery of salt and dust showed dry air intrusion in the northern wave environment. The effluent flow aloft and favorable deep layer wind shear and high moisture associated with the monsoon sustained convection in the southern wave environment, which led to the wave spooning a low center on the evening of July 3rd. On July 6th at 3Z, cyclogenesis happened, but in 42 hours, the tropical depression weakened to a tropical wave on July 7th, 21C. Since the first advisory of the Hurricane Center, this depression was not expected to intensify to a tropical storm, and advisories initiated based on well-defined circulation and persisting area of convection west of the center. I'm going to show now some of the looks of the Ghost 16 and Meteosat 10 imagery that we use to analyze this system. This is the RGB look from July 3rd, 2345 to July 9, and it shows the harsh thermodynamic environment that hinders further intensification of TD4. We can see how TD4 formed in the Central Atlantic on July 6th at 3C. Let me try to start the loop and show when cyclogenesis kind of happened. It was around this time where cyclogenesis happened, and then we can see, sorry about that, let me go back, And then we can see how the pink shaded area from the dust wrap around the system, and it weaken it back to a tropical wave on the 7th at 21C around this area. One of the infrared channels highly utilized at TAFB is the channel 13, or the clean long wave band. This particular loop shows how the cell, or the milky shade is of a cyclone, overtakes tropical depression 4, thus resulting in convective cloud tops warming, which led to disorganization of the deep convection on July 7. Another imagery that shows to be useful to monitor the interaction of the cell with the tropical cyclones is a low-level water vapor band centered near 7.3 microns. It highlights the mid-level moisture wrapping around the northern and west side of the system. The moisture is not easy to see with the legacy, with the Gold 13 water vapor, since its weight and function pitch much higher up in the atmosphere. This image is from Metasat 10. Let me replay it again. Here it shows like when the system weakens. And but going now to the convective products, one of the products that we utilized during the proving ground was the lighting density, or the GLD 360 from Vaisala, that it measures very low frequency radio waves, and it provides with a high cloud-to-ground detection efficiency, however limited intra-cloud detection. The frequency of lighting strokes is indicative of convective intensity, and in here I'm showing a case on March 25th, 2016, that it shows a strong offshore convection ahead of this cold front, producing severe thunderstorms, with the strongest updraft delineated by the pink shade, purple shades, and this storm may have been producing strong water spouts and dangerous winds for mariners in our offshore zones. Lastly, I want to show other of the products that we utilize heavily during the winter season, and one of them is the GeoColor imagery to the left. It shows ice clouds on white during day and night, and low clouds or fog or low stratus appears on pink during the night. And to the right, we have the Folklore Stratus product, that is a blended product merging satellite, numerical water prediction models, and daily sea surface temperatures, along with static ancillary data, and it provides fog probabilities on multi-cloud ledger scenarios, and it helps identify cloudy regions based on aviation flight rules. Here I show an example in our discussion where the Ghost IFR products show high probabilities of fog along the coast of Texas and along Mexico coast, and it has, this area has very low visibilities, which is very dangerous for small vessels and transit in this area. Some of the takeaways from utilizing this product is like the salt, the dust, and the pseudo-natural RGBs are useful for monitoring and tracking tropical waves. GeoColor imagery can be used alternatively to the pseudo-natural color imagery. Low-level water vapor can be used as an alternative to the dust and salt. Low-level LPW, or layer precipitable water, is valuable to examine convective environments for potential severe maritime thunderstorms or organization of tropical cyclones. The IR channel 13 is helpful for diagnosing the organization or disorganization of deep convection in tropical cyclones. And lighting density product has assisted us highly in diagnosing the threat of offshore convection where radar is not available. It is used to track convective cells beneath cloud shields, to distinguish thunderstorm from rain-only areas and identify strengthening or weakening of convection. The fog low stratus and GeoColor have shown to be important to issue fog advisories and warnings pertinent to mariners, which will help reduce the number of marine accidents in the Gulf of Mexico. This data is economically significant as commercial shipping industries rely on up-to-date weather data for critical decisions about routing ships around hazards. And that's all that I have. With that, I can take any questions you may have.
Any questions for Nelsie? Oh, okay, well, I'll throw in a question for you, Nelsie. I like how you showed the 7.3 micron water vapor imagery, and for these elevated mixed layer events where you have that dust, I would expect to see that in terms of a region of warmer brightness temperatures for these regions of elevated mixed layers. In other words, you have the deep mixed layer and the dust in those regions. So, because we use that channel for seeing elevated mixed layers coming off the Rockies as well, that play a role in terms of severe weather setups.
Okay.
Anybody else? Questions or comments for Nelsie? Okay, well, hearing none, we want to thank our presenter, Nelsie, for leading today's webinar. And our next webinar will be February 7th. Mike Baker from the National Weather Service in Boulder will talk about color tables in AWIPS. So thank you, everybody, and have a great day.
Thank you, Dan. Thank you, everybody.